that was symbolic. We have problems, we overcome problems. So let me begin. Thanks again for coming. It's very nice to see so many friends and colleagues, and to have this opportunity to share with you the very exciting prospects, I think, of TDLI Institute and physics into the future. It's appropriate to start by saying a few words about TDLI himself. He did remarkable work as a very young man, but even before he did his remarkable work in physics, he did remarkable work in preparing to be a physicist. He was born in Shanghai, but grew up in time of war, had struggles to keep educated. You can read about and look at artifacts from that period at the magnificent TDLI library here on campus, and I urge you to do that. It's a wonderful story. In this picture, you see the result of his struggles. He educated himself through the wartime, and in 1946, went to the University of Chicago to study with Enrico Fermi, and within a few years was a master physicist, and within a few years did revolutionary work, which won him the Nobel Prize at the age of 30. And in this picture with Xian Yang, you see shortly after they received the prize, some sort of magical icon of physics being done by young people. And this discovery of parity violation would be difficult to overestimate the significance of it for physics. It very quickly led to experimental confirmation at the hands especially of the Chinese-American physicist Madame C.S. Wu, and then to great progress in understanding the nature of the weak force, one of the four main forces of nature. Some of the problems it raised are still with us today. The kind of questions they asked about the symmetry between left and right. Today we're struggling with the symmetry between past and future. They pointed the way towards unification and modern physics. Afterwards, TD had many, many further achievements in physics, but also I think what makes him special is not only that, but is captured in this picture where you see the equations in the background and yet the personality shining through. TD was a very, very, and is a very, very warm person who has encouraged many young people and has become a kind of father figure to a whole generation in China and around the world. So let me now segue from TD as the inspiring spirit of this institute to its inspiring location and position in the world. China is, of course, a very ancient civilization with magnificent philosophies that are complementary to Western philosophies and cast new perspectives on reality, art, and every aspect of existence. And in recent years, China has become the engine of growth in the world. The extraordinary development of China has liberated many, many people from poverty, and China is now ready to take its place in the world as a leading engine of industrial and scientific development. Shanghai, even within China, Shanghai is even remarkable. Shanghai is a very vibrant city. You can see it in this picture. It's colorful. I was downtown last night and experienced this. There's just a sense of excitement in the air. It's on the water, it points out to the world, and it's also very popular. Lots of people like to live there, as you can see. Within Shanghai, we have a special university, the Shanghai Jiaotong University. This is what they have to say about themselves, and I assume it's true. It enjoys an increasingly high scientific research level and technology innovation level. 7th consecutive year, it leads the country, and this is objective, in both number of projects and amount of money issued by the National Science Foundation of China. And if you don't trust their self-testimony, we can also consult Wikipedia. Wikipedia says, one of the first national institutions of higher learning in China, and renowned as one of the oldest, most prestigious and selective universities in China. So, a great place, at a great, inside a great city, inside a great country, and the scientific world needs you. The scientific world has been, I think it's fair to say, for several decades, led by science, led by the United States, but the United States seems to be in the process of committing a kind of moral and intellectual suicide. We hope that that's an aberration, but in any case, it's important that the international scientific community look at other resources. So, the right place, the right time. Let me talk about what the TDLI Institute is actually doing. Oh, I'm sorry. Looking at the wrong version of this. Let me see if I can get the more recent version. Yes. It's still on 1. Sorry, I want 2. So you see science in the making here. Here is the Shanghai Daily of 24 February 2017, describing the commitment and the excitement within the city of Shanghai about what's going to happen. So there will be a science city in Pudong. Enormous resources are being put into it, enormous expectations are being raised, and this is the context in which the TDLI Institute finds itself. I'll just skip to the bottom quote, maybe you can read the rest. It says, the new center aims to enhance China's influence on the fields of fundamental physics, and then it goes on. The area, I won't attempt to, the Zhangjiang area aims to attract 500 renowned scientists and experts by the end of 2020. The scale of these things to someone coming from an environment where we argue over individual assistant professors endlessly is mind-boggling. Fu said, over 20,000 professionals from abroad, overseas graduates will work in the town by then. So, there's a lot of work to be done in order to live up to those resources, to live up to the potential of TDLI's spirit and the synergy of China, Shanghai, and SJTU. So in the last few days, here especially intensely, we've made ourselves a checklist of things to be done in the very short term, meaning weeks, nourishing our existing activities. We have already world-leading activities in dark matter searches, as you'll hear about, and in large-scale simulation of galaxy formation, in aspects of condensed matter physics. And we want to nourish those through programs and workshops. We want to form an excellent international advisory board. We want to build up international connections, in particular, build on existing connections with Sweden, and reach out to Singapore and other places, Korea and nearby. We want to prepare to make excellent appointments. We realize that it's going to be a process to make this new institution competitive with existing institutions. It's a non-linear process, and the first steps are the hardest, but we're going to go about it in a systematic, ambitious way. So we want to build up first-class physical and human infrastructure, spread the word, and look for opportunities. I hope you'll all tell your friends and young people that there are these opportunities opening up. I had gathering financial support on this list, but President Lin assured us yesterday that that's no problem. We're going to prepare an awe-inspiring event next year about the future of physics with leading experts and outreach to the public. And running sprints and marathons, this does not mean we're going to hold a physics Olympics. It means we're going to have focused kind of internal workshops on these, which areas to focus on, how to hold these events. And marathon means we're going to have continuing consultation once a week or once every 2 weeks to make sure that everything is on track. Including a consultation, including me, the president of the university, and a few select others. In the longer term, after we've done all the things on this checklist and got them up and running, our goal, of course, is to create a thriving center of research, which is world-leading in important directions, that is full of international collaboration, that does mentoring of the younger generation here in China and also through visiting programs with the rest of the world, and has cross-cultural activity featuring the kinds of connections between art and science that were so important to TDLI, and outreach to the public, because there's a hunger and a tremendous respect and admiration for science in China. And this will be very natural in the context of the Science City, which will not only be the TDLI Institute, but also other initiatives that are more applied. We will look to technology both as an inspiration for problems, for interesting problems, in the spirit of Bell Laboratories, and we'll be looking for applications of the technologies we develop in computing and sensing within technology. With all that, the primary objective is very simple to state. It's to do great science. So let me talk about that. We have 3 divisions, and I'll talk about the science connected with each division, just as a way of making the discussion organized. So particle physics and cosmology is one. Particle physics and cosmology today have a kind of fuzzy boundary. They're growing up together. Particle physics reached maturity in the later part of the 20th century. And we now have a powerful, compact core theory or standard model of the fundamental interactions that's adequate to give firm foundations to all forms of engineering, chemistry, astrophysics, and a lot, though not quite all, of cosmology. You can write it down on a t-shirt, and here's the experimental proof of that. here it is in detail to show that it really is an honest account of, an honest summary of our understanding of the basic laws of nature. Of course, you have to know how to unpack the symbols, but a computer could be taught this in a short program. Although it's mature, important challenges remain. In some ways, when a science gets mature, the nature of the problems changes, but it doesn't mean they become less important. The questions become more difficult, but also more ambitious, and the possibilities for application become richer. One great challenge is to understand the theory's riches, especially in quantum chromodynamics, QCD, which is the place in nature where both relativity and quantum mechanics get to work simultaneously. When those two get to work simultaneously, you have things like vacuum fluctuations. This is the fluctuations in gluon fields on time scales of 10 to the minus 24 seconds and spatial scales of 10 to the minus 13th centimeters or so. This is what your eyes would see if they had better spatial and time resolution, a kind of lava lamp. The numerical, although of course we can't see it, the numerical calculations that give us these pictures show us a deep structure of reality and have many other consequences we can check, so we know that they are correct. Heavy ion physics was another great love of TDLI, where the strong interactions produce collective phenomena and a richness of results that is quite inspiring. And it's not only inspiring kind of as an abstract proposition, but also because it simulates the conditions that prevailed in the universe close to the Big Bang. On the other hand, it fits on a t-shirt. Maybe we could fit it on a postage stamp. If we can further unify the forces to get still more compact descriptions, if we can increase the symmetry of the theory, there are brilliantly promising ideas that even have some circumstantial evidence for them, but to test them, we need more work at the LHC and beyond. So we will be exploring possibilities for further work of that kind in China. Here is the circumstantial evidence. If you include supersymmetry as a low energy, meaning sub-several TeV phenomenon, and calculate the evolution of forces following the formulas of the renormalization group and asymptotic freedom, you find indeed evidence for unification of the forces. But experimentally, it's much harder. It's much harder than doing little squiggles on a piece of paper. You can see here at the LHC, it's exhausting work. So far, the evidence has not confirmed that those ambitious ideas. However, it hasn't disproved them either. We just may need to work harder to get there. The astronomical dark matter is a phenomenon that is definitely there. It's the fact that there seems to be more gravity, more pull, more attraction of gravity in a variety of circumstances than can be accounted for by the kinds of matter we can observe using all the resources of astronomy. So electromagnetic radiation in all bandwidths, cosmic rays, absorption of light, none of those things seems to be affected, but there's something pulling matter around, and we call that something the dark matter. One of the most elegant demonstrations of dark matter, is its ability to bend light, and you get striking pictures like this one. This looks like you're looking through the bottom end of an old Coke bottle, but it's actually matter itself bending light. And if you calculate the amount of bending due to the objects that you can see, it's not enough to account for the gravitational pull on light that's observed. And there are many other pieces of evidence that point the same way. And so, despite the brilliant success of our core theory, it accounts for only the matter that makes about 5% of the universe, and we have a great challenge understanding what the rest of it is. We have promising questions, but no answers yet. We have candidates for what this dark matter might be that seem to theorists very promising. That would make our theories more beautiful if they existed, but as yet, no definitive answer. The Panda Experiment, which is sponsored by TDLI, is breaking new ground. They have the world record for limits on dark matter in certain parameter ranges. This is what the module looks like that does the detection. The site where this is carried out is an extraordinarily beautiful site. It's deep inside a mountain, which helps shield from various backgrounds. And that facility can be used in the future to do other groundbreaking fundamental studies of neutrino properties, deeper searches for dark matter, and others. So that is definitely on the agenda. Passing to astrophysics proper, it's an exciting time for astrophysics now. This is a very great time to be gearing up to do new things in astrophysics because new windows to the universe are opening. Large-scale surveys across the electromagnetic spectrum are becoming possible because of better sensing devices, but also because of computer power, which allows us to process vast amounts of information in real time. Gravitational waves have been observed now directly in the last couple of years, and more of that will be coming now that we know it can be done and what it takes. That's an activity that clearly is opening a new window on the universe. Recently, there have even been events that have been observed both in gravitational waves and simultaneously in electromagnetic signals. So clearly a huge new chapter of astronomy is opening up. These access some of the most violent and interesting events that take place in the universe. Neutrinos open another window that again is sensitive to violent and interesting events, some of them connected with QCD. Imaging has undergone a revolutionary evolution where now it's possible to image very distant objects, and in particular planets and other solar systems and black holes. And this is also opening up new windows on the universe, and perhaps the prospect of detecting life on other planets, perhaps the prospect of looking at gravity in very strong field environments. So interesting for fundamental physics as well as for just understanding what's out there in the world. There's a lot of synergy between astronomy and other frontier physics. So new detection and data handling technologies allow deeper, more complete exploration of the universe, because you can sample everything. You don't have to do it on a human time scale. You can do it much faster. And since there are billions and billions of galaxies out there, and each one contains billions and billions of stars, and the stars may contain tens of planets each, there's a lot to look at, and you can, with the help of powerful data processing, sense the particularly interesting and significant objects. This is a very similar problem to what happens in particle physics, where you have to, at the LHC, look at trillions of events to find the few that may hold clues for how to get beyond the core theory. early universe cosmology challenges fundamental physics. It produces, in the earliest moments of the Big Bang, the most extreme conditions that get beyond even what we can do with the most powerful accelerators. So it brings in access to processes that we can't study directly. We know some very, very peculiar things happened in the early universe, including the creation of the dark matter, including perhaps an epoch of cosmic inflation, and we don't really know what the underlying microphysics is. Neutron star mergers and supernovae bring in the equation of state of QCD at high density, and dynamic processes in QCD in regimes of high strangeness that can't be accessed directly in the laboratory, and so this is a great challenge for computation. And last but not least on this list, colliders and high power lasers bring heaven down to earth. Using those tools, such as the collider I showed you before, which had that explosion of events coming out that was producing temperatures of 10 to the 13th Kelvin and studying matter under those conditions. High power lasers can bring us to conditions in stellar environments that are also fascinating and poorly understood. So those are two of the components of the TDLI. The last is, in a way, less traditional and less well-defined, but I think is at least equally exciting and maybe even more vibrant these days. It's the frontier of quantum mechanics and understanding matter. Where by this I mean just, you know, you and me, ordinary matter, not dark, not extreme, just matter. Maybe very cold, in fact. Quantum mechanics is 100 years old, but it is still in its infancy. We can tell this because it's still growing and still surprising us like a baby. Just in the past few decades, we've discovered many, many qualitatively new states of matter, high temperature superconductors of several kinds, fractional quantum Hall effects, which bring in aspects of quantum mechanical correlations and topology and advanced mathematics that people wouldn't have dreamed were applicable to dirty matter before. Bose-Einstein condensates, topological insulators, spin liquids are now a frontier where it's not clear exactly even what they are, and how do you sense them and how do you deal with them, but the theoretical models are extraordinarily interesting, and there are indications of materials that fall into these classes. And finally, time crystals, which is my baby. You can see that it's broken through because it made the cover of Nature this March. And not only has it been a scientific breakthrough, but it's almost set a world's record for rapid commercialization. You can already buy time crystals on the internet. So new states of matter, they bring with them new phenomena, and there are also phenomena that have been unearthed without phase transitions, but fractional charge is one. We've learned that quanta, which the very meaning of the word is unit, actually can be unquantized. You can transcend sometimes the quantization of charge in particular. You can also transcend the quantization of quantum statistics. The worlds, the two kingdoms of bosons and fermions, we now know do not exhaust the possibilities for particle behavior, and that's become an enormous subject. We know now, we appreciate in ways that we didn't before, that the edges of materials are especially interesting. And can often supply different forms of persistent flows, which you can roughly think of as a vast generalization of the concept of superconductivity, where you have persistent flows of different kinds in many different circumstances. And new themes. Topology. You'll hear more about that this afternoon. Topology has become a gigantic specter in the world of condensed matter, and has been very fruitful in producing new concepts and generating new experiments. When I was a graduate student, if someone were asked what would be the most useless part of mathematics for physics, they might have answered topology, and it hasn't worked out that way. Entanglement, the fact that the Hilbert space is much, much bigger than classical phase space, has been a feature of quantum mechanics since the very beginning. But it's only now that we're learning how to navigate that larger territory within Hilbert space in a competent way, and learning that it's important to the behavior of matter, especially in these exotic states. And perhaps the deepest theme that's still taking shape is the emergence of information as the substrate of material behavior. Information has always been in the background within statistical mechanics as kind of the inverse of entropy, but now we're taking that into the quantum realm where new phenomena occur, very beautiful phenomena. All this, these new states of matter, these new effects, also involve new technologies. Perhaps, I think, the deepest, and certainly one that we hope to hone in on at the Institute, is the possibility of what I call calculated matter. The core theory gives us the laws. We know what the laws are. We know how quantum mechanics works. In principle, we should be able to put chemists out of business and just simulate what happens when you put molecules together. So that's certainly an inspiring proposition. You can also, of course, design matter to do useful things. This is not a new idea. The transistor is a glorious example of matter that was designed based on theoretical insight. The laser is another, but I think those are just the tip of the iceberg of what will become possible using quantum mechanics. Another technology that may even be synergistic with the first is the use of quantum mechanics as a computing, and entanglement as a computing resource. Hilbert space is very, very large. It can support parallel processing on a vast scale, can support memories on a vast scale, and if we can use those resources in intelligent ways, we can build new kinds of computers that will be very powerful. And perhaps the most powerful application of quantum computers will be that they'll be good at doing quantum mechanics. And so there's the possibility of a virtuous cycle where computations using quantum computers will enable you to build better materials, better quantum computers, and around it goes in an ascending spiral. Finally, I mentioned one more thing that's not quantum mechanical, but that's all right. We're broad-minded at this institute. The quantum wing can also do non-quantum stuff. A remarkable development in recent years that has involved people trained in theoretical physics as some of its most important figures has been the development of neural nets as an alternative architecture for computing. This is an important component in artificial intelligence. If you tap into Google Translate, or if you want to play Go against the best player in the world, which is an artificial intelligence, you're playing against a neural net. Neural nets are interesting not only as a powerful alternative architecture for computation, but because they are us in some sense. We have very capable neural nets inside our skulls that are very poorly understood at present. And the fact that neural nets have benefited from ideas of statistical mechanics and recently from ideas about dynamical systems, those are inputs to the most powerful architectures of deep learning and so forth. That means there's physics. Physics, I think, may help in that kind of thinking and experience, may help in understanding perhaps the most mysterious problem on the horizon of science, which is understanding how matter, the stuff that satisfies the core theory, manages to think. So I remember when I was a graduate student, this crazy picture from John Wheeler of the universe contemplating itself and understanding itself. And I remember thinking how ridiculous this was. But now that I'm older and wiser, I've come to appreciate it, and I think it very well summarizes or epitomizes the themes of this talk. We want to understand how, from the very smallest structures, the biggest structures evolve. We want to understand how computation allows you to trace this kind of evolution from a formless void to formation of structures and ultimately of mind. And by doing that, we will be looking at ourselves and our origins and understanding ourselves much better. Let me conclude then with a bit of calligraphy and a work of art. I hope I've persuaded you that there are exciting prospects in front of us and that the TDLI is well positioned to help humanity and help China and Shanghai and SJTU to take advantage of these opportunities. This bit of calligraphy says, roughly, very rough translation, is jade must be carved. If you have wonderful material, wonderful opportunities, you have the responsibility to make it into something useful and or beautiful. And that's the future of TDLI. Thank you. Okay. And that's my walk off.